Good morning, dear students. In the earlier class, you have learned the statement of work energy theorem and the proof of work energy theorem. What is the statement of work energy theorem? The net work done on your body is equal to change in kinetic energy of the body. So we proved work done on your body is equal to change in kinetic energy, that is final kinetic energy minus initial kinetic energy. You also learned potential energy, the definition of potential energy. What is that? Energy associated with position is called potential energy. You also learned the general equation for gravitational potential energy. So for gravitational potential energy, we use the formula mgy. So we take a reference point here, ground as a reference point. So ground as a reference point. When we take ground as a reference point, the formula for gravitational potential energy is mgy or mgh. Here y or h is the height of the object above the ground. And you also learn the statement of the definition of conservative force. A force that offers the opportunity of two-way conversion between kinetic energy and potential energy is called a conservative force. A force which offers the conversion of potential energy to kinetic energy and kinetic energy to potential energy, that force is called as conservative force. A good example for conservative force is gravitational force. And you also learn the properties of work done by conservative force. So we have three properties. The first one is the work done by conservative force can always be expressed as the difference between the initial and final values of potential energy function. And the second property is the work done by conservative force it does not depend on path, it depends only on initial point and final point. And the third property is the work done by conservative force along a closed path is equal to 0. And an important point which we should remember, that is, when conservative forces only do work on a body, the total mechanical energy of the body remains constant. A good example is freely falling body or vertically projected body. So for this body, what happens? Its total mechanical energy remains constant. So when a body goes up, its kinetic energy decreases but potential energy increases. When the body falls down, its potential energy decreases but kinetic energy increases. But the sum of these two energies remains constant because only gravitational force is acting, which is a conservative force. So in this class, now we derive the equation for potential energy stored in a spring, which is also called as elastic potential energy. Yeah, first we should know Hooke's law to derive the equation for potential energy stored in a spring. First we should know Hooke's law. The statement of Hooke's law: the elongation or compression of a spring is directly proportional to applied force. Yes, this is the statement of Hooke's law. Now to explain the Hooke's law, now take a spring and a block system. Yeah, this. Here we have a rigid wall. One end of spring is connected to a rigid wall and other end is connected to a block. And a smooth surface. Smooth surface means frictionless surface. For our convenience, we are taking a frictionless surface. So let's say initially the block is here. Let us call this point as x equal to 0. Now let us move the block from here to here. By applying some force this way, let us move it. That means let us stretch the spring. Let us stretch the spring. And this is the actual path we have. Now we are stretching the spring from here to here. Let's say this is x. X is the displacement in x direction. So in what way we are applying force? Yeah, we are applying force in this direction. We applied. Now here I write the extension. As we apply more and more force, what happens? This extension also increases. Na? So according to Hooke's law, what do we write? The extension of the spring is directly proportional to applied force. So as we apply more and more force, what happens? This x value increases, isn't it? Yes. But hold here, by applying some force here, hold here, and if we leave this body, if we remove this applied force, what happens, guys? Does the block stay here? No, the block moves this way, right? That means there is another force which is acting this way. there is another force which is acting this way, which is called spring force. This force is also called as this force, this vector. This force is also called as restoring force. Restoring force. Spring force is also called as restoring force. Whenever the applied force, the magnitude of applied force and the magnitude of spring force same, so then the block is at rest. If you remove this applied force, what happens, guys? There will not be this force. Only because of the spring force, because of the restoring force, the block accelerates backward direction. That means Hooke's law can be written in both ways. One is in the form of applied force, that is applied force is this way and extension is this way. But we can also write Hooke's law in terms of restoring force also, that is spring force. So when you, in some books they write minus x, the minus x comes here. So spring x equal to minus x, because so x is pointing this way but the spring force is pointing in the opposite direction, right? That means Hooke's law can be written either like this or like this. So this is in terms of extension and applied force. This is in terms of extension and restoring force. Extension ఇటువైపు ఉంటే ఏమవుతుంది, the spring force will be this way. And when the spring is compressed, now you can take like this. Now here we are compressing the spring. We are compressing the spring. That means extension of the spring is this way or compression of the spring is this way. And how do we apply force? We push it this way. So applied force is this way and the compression of the spring is also this way. But if we remove this applied force, what happens, guys? Does the block stay here? No, it moves toward the mean position, right? That means mean position or this point, this initial position is called as mean position or equilibrium position. If you remove this force, again the block accelerates toward this way. That means there is another force acting on the body, so which is called as spring force, or it is also called as restoring force. So because of this restoring force, what happens? The block moves toward this way. Again in this case also, what's happening? Applied force and compression of the spring, both are in the same direction. But what about the spring force or restoring force? Spring force is this way, but the compression of the spring is in the opposite direction. That means, so when you write extension or compression in terms of restoring force or spring force, you are supposed to use minus sign. But when you write extension or compression of the spring in terms of applied force, we need not to use minus sign here, because both are in the same direction. But here spring force and extension or compression, so these two are in the opposite direction and these two are in the opposite direction. And here these two are in the same direction, these two are in the same direction. So when you use applied force, so we take these two. When you take spring force or restoring force, we take this combination. Now we remove this proportionality and here we take a constant F applied. F applied is equal to, we remove this proportionality and here we take a constant K. And here also restoring force or spring force, whatever you call, is equal to, we write minus Kx. Don't get confused. Sometimes we write F equal to Kx, F equal to minus Kx. That means if we write Kx, that means the force is applied force. If we write F equal to minus Kx, that force is restoring force or spring force. Hope you understand this one. Yes, here K is called as, here K is called spring constant. It is called spring constant. And units of K, if we keep K here and bring this X here, for force what is the unit? Newton. For X, this is compression or extension, that is displacement only, right? So meters. So Newton here, take K equal to F. K, if we keep K here, it becomes F by X. So unit of K is Newton per meter. This is the SI unit we have. And we also have another unit, that is Dyne per centimeter. Usually we don't use that one, we use Newton per meter only. Yes, now let us derive the relationship between work done by the spring and elastic potential energy stored in the spring. So for that one, now consider a spring attached to a block and a smooth surface here. Now let's say initially the block is at x equal to 0. Now let us stretch the spring. That means by applying force on the block, let us move the block this side. So let us move, let's say we are moving the block, let's say this is initial x equal to 0, let's say this is position x equal to x1, and assume this is here, and we are starting, we are extending, we are holding the block, and we are moving like this. So we are moving, first we are moving till x1, then we are moving till the block moves towards the position x2. That means initial position of the block is x1 and final position is x2. That means, so from here to here, initial extension is x1 and final extension is x2. That means actually we are moving the block from x equal to 0 to here, but we are taking this one as initial position and this one as final position. Now let us calculate the work done by the spring, as the block moves from initial position x1 to final position x2. Work done by the spring. Work done by the spring. Work done by the spring on the block. As it stretches from x1 to x2. Now W, total work done. Yes, see guys, here the spring, does it exert a constant force as it extends from x1 to x2? No, because clearly what do we have? F applied or spring force is equal to, what do we have guys? So it is proportional to x. That means as the extension value increases, the magnitude of spring force also increases. As x value increases, magnitude of spring force also increases. Now can we use the formula, the scalar product of force and displacement directly? No, but here you can take as a whole, you cannot use, here force is not constant from x1 to x2, but take a small displacement dx. For that small displacement, force is constant. So we calculate a small work done. Fs into dx bar. So we calculate a small work done, Fs into dx bar, but we want to calculate the whole work done from x1 to x2, right? So what do? We do integration. This is the small work done, but if you want to calculate the whole work done from x1 to x2, we do integration. So initial value is x1, final value is x2. Yes, now, yes, in the next step, what do we write here? Fs, so magnitude of Fs, magnitude of dx bar. See guys, here what is the angle between Fs and dx? Spring force. So we apply force and the applied force will be in this direction, F applied. But what is the direction of spring force or restoring force? So we are calculating work done by the spring. So here spring force will be in the opposite direction. So spring force acts toward this way, but the small displacement is this way. So what is the angle between force and displacement here? Small force and small displacement. This is Fs is instantaneous force here, and the angle between these two vectors is 180 degrees, and the lower limit is x1, upper limit is x2. Why 180? Fs spring force is acting this way and displacement of the block is this way. So the angle between these two is 180 degrees. So cos of 180 minus 1. Now we will continue the derivation. Yes, we will continue the derivation. So integral x1 to x2. So what do we have? Magnitude of spring force into magnitude of dx bar into cos of 180 degrees. And magnitude of Fs, spring force. Yes, first cos of 180, what do we write? Minus 1. Let us write minus 1 here. And magnitude of Fs, actually spring force equal to minus kx, but we are supposed to take magnitude, right? So kx into dx bar. So we take only magnitude, and lower limit is x1 and upper limit is x2. Now minus is common, k is a constant, right? So k, take it out, and integral x1 to x2 x dx. How does it look like? Integral x power n dx. X power n in the position of n, what do we have? We have 1. So minus k So x power 1 plus 1 by 1 plus 1. Lower limit is x1, upper limit is x2. So minus k, first we substitute x2, x square, right? X square by 2. So x2 square by 2 minus x1 square by 2. Now, so work done by spring is equal to, what are we getting? Minus of kx2 square, minus into minus plus of kx1 square. So work done by spring, that means the unit of this quantity must be joules, right? Then what should be the unit of this quantity and this quantity? The unit of this quantity must be joules and the unit of this quantity must be joules. Joules means, so this quantity should represent energy and this quantity should represent energy. And the terms which we are getting here, what is k? K is a spring constant. It belongs to spring, right? And x1 and x2. x1 is the initial extension and x2 is the final extension. That means this is the energy. We are clearly, this term is indicating energy and this term is also indicating energy. And x1 is called position, right? Extension means it represents positionally, right? That means this is the potential energy and this potential energy belongs to whom? Spring. That's why this potential energy is called as elastic potential energy. Here the term of kx square or x1 square or x2 square, here this term is called elastic potential energy. So elastic potential energy, U spring, we also write U elastic is equal to, we can write a general formula of k x square of kx square. Now from this equation, work done by the spring, now take minus common. If we take minus common, from this equation I am taking minus common of kx2 square and this becomes minus, right? Minus and minus plus, if we take minus and minus, it becomes plus of kx1 square. Now what is this? This is the final elastic potential energy and this is the initial elastic potential energy. Minus work done by spring is equal to final elastic potential energy, elastic EL, initial elastic potential energy. So clearly what do we write? This value is nothing but final minus initial, that is nothing but change in potential energy, right? So work done by spring is equal to the negative of change of elastic potential energy. How does it look like? Work done by gravity is equal to the negative of change of gravitational potential energy. These two are similar, right? These two are similar. So there we get work done by gravity is equal to the negative of change of gravitational potential energy, and here work done by the spring is equal to the negative of change of elastic potential energy. I told you that gravitational force is a conservative force. In the similar manner, the force exerted by spring is also a conservative force. Here we explain like this. Now consider a spring which is attached to a block here and x equal to 0. Now move the block from here to here and leave it. Some x equal to a. Stretch the spring from here to here and leave it. What happens? Does it stop here? No. It moves toward this way. So because the spring exerts force this way, it moves toward this way. And does it stop here? No. So as it moves from here to here, the block gains some kinetic energy and here the block will have kinetic energy. So it compresses the spring. So it moves toward this way and until it moves x equal to minus a. And does it stop here? No. Again the spring exerts force this way and again it moves this way. So whenever the block moves here, the block will have kinetic energy. So because of inertia, so it moves towards this way and again it moves towards x equal to plus a. So it oscillates, the block oscillates between x equal to plus a and x equal to minus a. When it oscillates, what's happening? Whenever the block is at positive extreme, it has maximum potential energy. And whenever the block moves towards mean position, the potential energy becomes 0 and it will have maximum kinetic energy. And does it stop here? No. Again the block moves toward this way. As it moves toward this way, its kinetic energy decreases and potential energy increases. Whenever the block reaches negative extreme, that is minus a, so the block will have, the spring will have maximum potential energy and the kinetic energy of the block becomes 0. So in this process, what's happening? Kinetic energy of the block is converted to potential energy of the spring and potential energy of the spring is converted to kinetic energy of the block. So two-way conversion is taking place, right? So that means the force, because of this, the spring force only, this thing is happening. The conversion between potential energy of the spring and kinetic energy is taking place. So the spring force is a conservative force. And we also have properties of work done by a conservative force. We have three properties, right? So work done by a conservative force can be expressed as initial potential energy function minus final potential energy function. Yes, here you can write. So work done by spring is equal to, you can write, yeah, here you can write, yeah, if you take this minus common, so work done by spring is equal to, actually you can write UL1 minus UL2. When you take minus common, we are getting like this. But if you don't take minus common, what do you get? You get initial elastic potential energy minus final elastic potential energy. This is the first property. And what is the second property? The work done by a conservative force does not depend on path. It depends only on initial point and final point. The same thing happens here. And here also the work done, when it moves like this, when the block moves from positive extreme to mean position directly, or positive extreme to negative extreme and comes to mean position, in both cases the work done is same. When initial position and final position are same, so the path followed, the work done by spring does not become same, whether it comes directly from here to here or when it goes negative extreme and comes to this position this way. In both cases the work done by the spring is same. And the third case, and the third property, the work done by conservative force along a closed path is equal to 0. Suppose the block is starting here and it is moving towards negative extreme and it is coming to positive extreme. So the work done, whole work done by the spring is 0, because so the work done by the spring from here to here is positive, because the spring force exerted by the spring is this way and the displacement of the object is also in this way. So from here to here the work done is positive. But what about the work done from here to here? The block moves toward this way, but the spring exerts force in this direction. So from here to here the work done is negative. And when the block moves from here to here, work done by the spring is positive, because the force exerted by the spring is this way and the displacement of the spring is also this way. And when the block moves from here to here, the force is this way and the displacement of the block is this way. So totally here, if the work done by the spring from here to here is plus 100 joules, then the work done by the spring from here to here is minus 100 joules. And again, when the block moves from here to here, the work done will be plus 100 joules from here to here. When the block moves from here to here, the work done will be minus 100 joules. Then it is completing a complete path, right? This is called a closed path. Now what is the total work done? Plus 100, minus 100, plus 100 and minus 100. So the total work done becomes 0. That means the work done by spring force is also satisfying the third property. So that's why, so spring force is a conservative force like gravitational force. So till now how many examples we have for conservative force? 2 examples. So one is gravitational force, another one is spring force. And we also remembered an important point regarding conservative force. Only whenever a conservative force only does work on a system, the total mechanical energy of the system remains constant. So here you can take, so take the block here and stretch the block from here to here and it leave it. What happens, guys? It oscillates. Suppose if it is x equal to plus a, so it moves until x equal to minus a and so on. If it is a smooth surface, if elastic force, that is spring force, only the force acting on the body, so the block oscillates like this. The block oscillates in between plus a and minus a. While it is oscillating, what's happening? So potential energy is converted to kinetic energy of the block, kinetic energy of the block converted to potential energy, but the sum of these two energies remains constant. At any point the total mechanical energy remains constant, because the spring force is only doing work on the system. So spring force is a conservative force. We know whenever conservative forces only do work, the total mechanical energy of the system remains constant. Yes. So here we can say the spring force is a conservative force. So when a block is connected to a spring, the total mechanical energy of the spring block system is conserved. That means the sum of kinetic energy of the block and the potential energy stored in the spring always remains constant. If this value increases, this value decreases. And if this value decreases, this value increases, but the sum of these two energies always remains constant. Yes. Now let us take EX graph. The graph that is drawn between energy versus position. X means extension or compression of the spring. Now we take like this. So we are taking x value and we are taking energy value. Now I will explain. Yeah, here by taking the block also we can write by, let us show block also here. So initially the block is here, x is equal to 0, x equal to 0. Now we are stretching the block from here to here, that is x equal to, let us call xm, maximum displacement here. So whenever the block is stretched, whenever the block is moved or the spring is stretched, what happens guys? Whenever we leave, initially the kinetic energy of the block is 0, but there is a maximum energy stored in the spring, right? That is potential energy. So potential energy is maximum here and kinetic energy is 0. Kinetic energy is 0. Now here I take energy. Energy at this point, the energy will be maximum, isn't it? Energy will be maximum. I am taking only potential energy. So initially potential energy, whenever the block is here, that means the spring is extended. The spring is extended till this point. So at this point potential energy is maximum, right? And as the block moves toward this way, what happens guys? The potential energy decreases, and it becomes 0. It becomes 0 whenever the block comes to here. And does the block stop here? No. Again, the spring is compressed here, and until x equal to minus xm. So again, so if this point is minus xm, this is plus xm and this is minus xm. So whenever the block moves from mean position to this way, the spring is compressed, right? The spring is compressed. So whether x value is positive or negative, so what is the potential energy stored in the spring? Half kx square. So whether x is positive or negative, so potential energy stored in the spring is negative. So again it increases, and it becomes maximum like this. Let's say this is the minus xm. So we get graph like this. When you take the graph between potential energy, yeah, this graph indicates potential energy versus x. Now let us take kinetic energy. So at x equal to xm, whenever we leave, what happens to the kinetic energy? Guys, kinetic energy becomes 0, right? So on here you are taking energy. So x equal to, when x equal to xm, so kinetic energy is 0. But as the block moves toward this way, kinetic energy increases, and whenever the block reaches mean position, kinetic energy becomes maximum, and you will get like this. You will get maximum here, and whenever the block moves from here to here, its kinetic energy decreases and finally it becomes 0. So here it becomes 0 like this. It becomes 0. So this graph indicates kinetic energy versus position, and this graph indicates potential energy versus position x. But whenever you take the sum of these two energies, potential energy and kinetic energy, the total energy remains constant. The total energy remains constant. So total energy TE is equal to PE plus KE. Whether the block is here or here or here or here or here or any point, at any point, the sum of potential energy and kinetic energy, that always will get a straight line from here to here, or from here to here, this total energy remains constant. So this graph, this straight line indicates total energy, this graph indicates potential energy, and this curve indicates kinetic energy. But the straight line from plus xm to minus xm, we get a straight line. This straight line indicates total energy because the total energy remains constant. Now let us find the maximum speed. Of spring. Maximum speed of a block. Finding maximum speed of block. Yes. So when the block is left here, initially its kinetic energy, its velocity is 0. But as it moves toward this way, at mean position, what happens guys? The block will have maximum speed now. And whenever it moves toward this way, the spring exerts force in the opposite direction, so it slows down and finally it comes to rest here. But at which point the body has maximum kinetic energy? At mean position. At mean position, the block has maximum kinetic energy. But what happens to the extension or compression of the spring x equal to 0? So the potential energy stored in the spring becomes 0. That means here we can apply conservation of energy. So at this position, there is no kinetic energy, and there is a maximum potential energy stored in the spring. At this position, the block has maximum kinetic energy, but the potential energy stored in the spring becomes 0. That means here, if the potential energy stored in the spring is 100 joules, whenever the block moves from here to here, the kinetic energy of the block becomes 100 joules, because there is no potential energy stored in the spring. That means the total potential energy is converted to kinetic energy. Now on applying conservation of energy. Yes, maximum kinetic energy, that is half mvm square. Maximum kinetic energy at mean position is equal to maximum potential energy stored in the spring at negative extreme or positive extreme, that is half kxm square. This value is if 100, and this value will be 100. That's what I am telling. Now our intention is to write the equation for vm square. Vm, not vm square. So vm square equal to half gets cancelled, kxm square by m. Now vm is equal to, yeah, you can take xm here, square root of k by m. This is the equation that we use. Xm is the maximum displacement in positive direction, and k is the spring constant, m is the mass of the block. By using this equation, we can find the maximum speed of the block. Given k value should be given, that is spring constant should be given, mass of the block must be given, and maximum extension of the spring must be given. Then we can find the maximum speed of the block at mean position. Yes, now let us see various forms of energy. The very first one is heat. What is heat? Heat is a form of energy which flows from higher temperature to lower temperature. If a body is at higher temperature, heat flows from that body to surroundings, or if we have another body which is at lower temperature, the heat flows from higher temperature to lower temperature. Next one, chemical energy. So whenever chemical reactions takes place, heat may be absorbed, heat may be released. So the reactions in which heat is absorbed, the reactions are called endothermic reactions, and the chemical reactions in which heat is released, the type of reactions are called exothermic reactions. So if you want to produce energy, if you want to use energy, so which type of chemical reactions do we need? So that is exothermic. A good example is burning of coal. If we burn 1 kg of coal, we get energy, this much amount of energy. If we burn 1 kg of coal, so we will get this much amount of heat energy is released. That means which type of chemical reaction is burning of coal? That is exothermic. That chemical reaction is exothermic. And the third one, electrical energy. What is electrical energy? So what is the use of this electrical energy? We use many electrical appliances, right? TV, fan, fridge, and so on. We have many things. So all these work with only electrical energy. So charges carry energy to the electrical appliances, and they give energy to the electrical appliances, and they work. So here electrical energy is used by the electrical appliances. Yes, the equivalence of mass and energy. Till 19th century, scientists used to believe that mass is conserved in any reaction. Mass is conserved in any reaction. And they thought that there is no relationship between mass and energy. But Einstein proved that mass and energy, these two are equivalent. That means mass can be converted to energy, and energy can be converted to mass. He gave an equation which is called as mass energy equivalent equation. So according to that equation, E equal to mc square. E equal to mc square. Here m is the mass and c is the speed of light. What is the c value, guys? 3 into 10 power 8 meter per second. That means if we have m equal to, if take 1 kg of mass, if we can convert 1 kg of mass into energy, so the amount of energy which we get is E is equal to 1 into c square, that is 3 into 10 power 8 square. So how much do we get? T square, that is 9 into 10 power 16 joules. So we can get this much amount of energy. If we can convert 1 kg of mass into energy, we'll get huge amount of energy. But manually, can we do this one? Manually we cannot do, isn't it? So this thing happens. So this mass is converted to energy. This thing happens in the case of whenever nuclear reactions takes place. So mass is converted to energy. That I will explain now. Yes. So nuclear energy. A nuclear energy is nothing but this one, the equivalence of mass and energy. Usually, if nuclear, we have two types of reactions: nuclear fission and fusion. In nuclear fusion, what happens is we have uranium atom 23892. It collide with a fast neutron. And it produces barium and krypton. It also produces some energy. Whenever this chemical reaction takes place, energy is produced. The reason is we get energy here, right? The reason which we get energy here is, so energy equal to what happens is, so the mass of the reactants and the mass of this product, these two are not same. So when we see the mass of this reactants is greater than mass of these products, that means certain amount of mass is lost, right? Just I'm telling example. Suppose if the mass of this whole thing is, let's say, 1 kg, the mass of this reactants which we get, the value will be 0.999998 kg, like this. That means a little difference is there, right? So whatever the mass is lost, that mass is converted as energy. So here delta m, how do we calculate delta m? The mass of this thing minus mass of products, mass of reactants minus mass of products. So we'll get some value, right? Now energy produced in this case is equal to, what is the formula? Delta m into c square. If delta m is equal to 0.00001 kg into c square, that means I'm telling 1 kg, and this value is not for only one reaction, for many reactions, for crores or millions or billions of reactions. So for these many number of reactions, the value may be this one. If this is 1 kg and this value may be this one, so in that case, if this value is 0.2 kg, the difference is 0.002 kg. So 3 into 10 power 8 whole square. By using this equation, we will get energy. Hope you understand this one. That means, so mass of these products is always less than mass of reactants. So certain amount of mass is lost. So that loss of mass is converted to energy in nuclear reactions. So by using this equation, we can convert, so the whatever the amount of mass is lost, that is converted to energy. By using this equation, we can find the amount of energy released. Now the principle of conservation of energy. This one you have already learned. Energy neither be created nor be destroyed. It can be converted from one form to another form. If you take any energy, that may be kinetic energy, potential energy, sound energy, light energy, heat energy, water may be the energy. So whenever some energy is lost, so that energy is converted to some other energy, but the total energy remains constant in the universe.